there are two different kinds of projectile motion problems that are very easily modeled by a quadratic equation. The first type is when an object is simply dropped from a particular height. The second is when an object is launched in the upwards direction with an initial velocity identified in the problem, where the object will travel upwards and then back downwards. In this example, that's exactly what we have. Because we have an initial velocity for the object of 30 feet per second, we can use that initial velocity and the initial height that the ball is launched from and write a quadratic model where the height is dependent upon the time the ball is in the air of negative 16t squared plus 30t plus 4. Now, this model is limited in its potential real-world application. This assumes that the only force that is acting upon the ball is a gravitational force, where if the ball is thrown up, gravity is pushing down on the ball, so the ball will have a parabolic path. If there's things like wind or any kind of debris in the air, or it's particularly humid on that day, the ball will not travel according to this model exactly. But this is a rough approximation for most of the scenarios of the ball's path in the air, the height of the ball as the ball is released. Now, beyond just simply writing the quadratic function, we have a question of, can you determine when the ball is a particular height in the air? So how long will it take for the ball to be 10 feet off the ground? How long will it take for the ball to be 25 feet off the ground? Both of these can be solved by writing equations. 10 is our height, and we have our projectile motion equation. 25 is our height, followed by the same projectile motion expression. Both of these can be set equal to 0. And at this point, we run into a little bit of an issue, because is this really the most efficient way to test whether or not the ball, or when the ball reaches these particular heights? We're going to have to use the quadratic formula. There's not a lot of easy factoring, it looks like, in order to determine at what times the ball reaches those heights. This is a situation where it might be easier to transition to the graph of this function and be able to look at potential intersection points between this function and these two heights. That doesn't mean you couldn't use the quadratic formula on both of those equations in an attempt to solve them. It just means that maybe there's a more efficient option. So let's transition to the graph. That's what we're going to see here. And we have a want of when is the ball going to reach a height of 10. So we have two intersection points. We have one right here at 0.228 seconds and one right here at 1.647 seconds. Our other location that we were interested in was how long will it take for the ball to be 25 feet off the ground? Well, it looks like from this graph, and we need to zoom out a little bit to see this, we're never going to be 25 feet off the ground. Despite the fact that we launched the ball at 30 feet a second from a height of 4 feet, that's our intersection, our y-intercept over here. That velocity and that initial height do not allow me to reach that height of 25 feet. Which means when we would solve these two equations, we should expect this discriminant to show us that there will be two real solutions. But this discriminant, we would anticipate, would show us no real solutions. No solutions over here because the ball's never 25 feet off the ground. Two solutions here because the ball reaches that 10 feet off the ground at two different times.